Okay, so today again we begin a new lecture, and we will continue on X-ray diffraction, which we started in the last class. Let me just begin with a bit of recap of the last lecture. We were talking about, so we finished discussing the structure of materials, concluding with the structure of polymers. So in this lecture we started talking about X-ray diffraction. And basically diffraction effects were discovered earlier by Thomas Young's double slit experiment, and where he concluded that d and lambda is equal to d sin theta is a condition to be met for diffraction to occur with n being an integer. So he, following that, there was a concept of constructive and destructive interference. So when waves, when they pass through an obstacle, they undergo diffraction, and when the amplitudes of the wave add up constructively, then there is a maxima observed in the diffraction pattern, and when at other angles, when they do not add up constructively, there is a destructive interference. As a result, there is no diffraction that takes place. So following this, the experiments which were conducted by Young were on slit spacing, which were of the order of visible light wavelength. Now atoms in crystals, if they are arranged periodically, they can be considered as slits. However, the spacing between those slits is as small as 2 to 3 angstrom, something like that. 2 to 4 angstrom, 5 angstrom is the typical lattice parameter of materials, which requires you to, so the condition n lambda is equal to 2d sin theta or d sin theta in Young's experiment. It allows, it tells you that lambda and d should be comparable, because sin theta cannot be more than plus or minus 1. So if you want to get the diffraction effects from crystals, you need to have a radiation whose wavelength is comparable to the lattice spacing in the crystals, and that is where X-rays were useful after they were discovered. So X-rays, so we talked about X-rays, how they are generated. So basically we looked at when you eject a K-shell electron, when a high energy electron beam bombards a target, let us say copper in this case, then high energy electron beam ejects a K electron, if it is high energy, if it is high enough in energy, then this K electron which has been ejected, it leaves a vacant place there. Now this becomes excited state. As a result, it becomes an unstable configuration. As a result, the electron from the higher energy level has to go down, and it can make a transition from L level, it can make a transition from M level, it can make a transition from N level, and there is a probability of transition, and it turns out that the probability of transition is highest from the L level than if the transition has to happen to K level, then it is more probable that electron will come from the next level rather than from the further levels. So that is how these transitions occur, and they give rise to, when the electron from higher to lower energy undergoes a transition, it emits a X-ray photon, and this X-ray wavelength, that X-ray corresponds to the energy difference between the two energy levels. So if it is K alpha, then for K alpha it is going to be the energy difference between the EL minus EK. Okay. So this is what is going to be the, so we looked at, so you can have, so if this is your K shell and this is your L shell, then L shell has 3 shells. Okay, so this is L1, this is L2, this is L3. So typically the transition which is made from L3 level, that is alpha 1 transition, and transition from L1 and L2 are quite close to each other, they are designated as alpha 2 transitions. This is the signature. So this In this case it will become K alpha 1, in this case it will become, and accordingly you will have L alpha, M alpha and so on and so forth. Now we then looked at the spectra after bombarding. The spectra is sort of, it varies in this fashion. So as the kV increases and so this is lambda, this is intensity of radiation and this is kV increasing. Okay. So this could be, let us say, at 25 or 30 kV, and this could be, let us say, at 20 kV and so on and so forth. So what you have here is 15, 10, and if you have 5 it will be. Now what happens is that you get at lower voltages you get a radiation of wide wavelengths, which is called as continuous radiation. At higher kVs you start getting characteristic radiation, which is, in this case it could be K beta, this could be K alpha, and this is what is very useful for X-ray diffraction to occur because it provides you high intensity, and the limit of wavelength is called as lambda SWL, which I showed you in the last class. This is equal to HC divided by EV, which turns out to 12,400 divided by V in volts.
What happens to that K electron?
Sorry?
What happens to that K electron?
So that K electron gets emitted, it goes out of the material,
Okay.
and as a result you have transition from the higher level. So the whole idea in X-ray diffraction is to use these characteristic radiations for typically we use K alpha radiation for X-ray diffraction analysis, because K alpha radiation has a wavelength which is comparable to lattice parameters, and it has an intensity which is very high intensity. So you do not have to go to very high kVs to achieve good signal to noise ratio. So it provides you very good signal to noise ratio as well, and most of the X-ray diffraction is carried out using monochromatic radiation, unless you are dealing with single crystals. If you are dealing with single crystals, then typically you use white radiation or continuous radiation, whereas in case of polycrystalline materials typically we use monochromatic radiation, and that is where we choose K alpha in most cases. And this K alpha, choice of K alpha radiation, typically K alpha 1 is the one which is chosen. So we can use copper, we can use moly, we can use chromium. These are some targets which are typically used in X-ray diffraction. So another thing which happens is that when X-rays strike a material, then X-rays undergo absorption. Okay. When X-rays undergo absorption, of course the intensity changes as a function of I is equal to I naught exponential of minus mu by rho into rho x. Okay. This is mass absorption coefficient mu rho. So the rho x, if you plot the mass absorption coefficient as a function of wavelength, then typically it shows behavior which is like this. So this basically is the point where absorption suddenly decreases, depending upon how you look at it. This is called as absorption edge. This can be basically this is the absorption edge, corresponds to the energy when the energy becomes E is greater than Ek, when energy of the incident photon is higher than the K binding energy. So the moment it starts, its energy is higher than the K binding energy, which means it can eject K electron, but at the same time which means that the energy is absorbed, because now energy is spent in ejecting the K electrons. So which means the incident radiation will lose its energy if, so basically let us say if this is a certain material, in this case let us say iron. If it is the case of iron and you are bombarding iron with something, then or you can use this, let us say this material is, let us say, nickel. Okay. It turns out you can use this absorption edge to suppress certain radiation and to allow certain radiation to go through. So, for example, in case of copper, the K beta radiation is somewhere here, okay, and K alpha is somewhere here. Okay. So, it turns out that if you want to use K alpha predominantly, you let the X-rays pass through a nickel filter, okay, because nickel has a K absorption edge. This is K alpha, Ka of nickel. Nickel has a K absorption edge which falls between. So, this is, let us say, K beta peak of copper, and this is K alpha peak of copper, okay, K alpha Cu, and this is K beta Cu. So, if you want to use copper radiation, and you want to use K alpha component, then you let copper radiation pass through a nickel filter. What nickel filter will do, and this is, by the way, logarithmic axis. Okay. So, this is, these scales are logarithmic in nature, log plot. So, which means the decrease or change is substantial. So, when copper radiation Cu passes through a nickel filter, then nickel absorbs K beta component and it allows K alpha to pass through, because K alpha gets absorbed lesser than K beta. As a result, what you get out of the system is predominantly K alpha. So, this absorption edge properties of materials can be used in using one use of this absorption edge property is to choose a material which can be used as a filter to give you the wavelength that you want for the incoming radiation. Okay. In case of copper radiation Cu K alpha, we typically use nickel filter, because nickel has a absorption edge which lies between nickel K absorption edge lies between Cu K alpha and Cu K beta. So, such that E Cu K beta is higher than E K of nickel, higher than E Cu K alpha. So, basically it will absorb this, but not that, all right, okay, because you see the lambda has a different relation, the lambda is on the higher side. So, which means lambda of Cu K alpha is higher than the lambda corresponding to the absorption edge, which means the energy of the absorption edge has to be higher than the energy of the Cu K alpha. So, energy of the absorption edge, this is the absorption edge of nickel, this energy is higher than the Cu K alpha, but it is lower than Cu K beta, which is where it has high absorptivity, high absorption for this thing. Another thing that you need to now, since this absorption takes place, the X-rays which come out of material, the X-rays which are emitted, those X-rays also have X-rays which are incident on the material. So, when you have X-rays incident on the material in such a fashion, so that let us say if you have energy levels like this, okay, and these X-rays, when you have X-ray incident on a material, it can excite electron from the lower energy levels. As a result, this electron goes there and the energy levels here, so this was filled, this electron now makes a transition to this level. So, this becomes empty and this gets filled, which means it will emit a wavelength which is h nu prime, where h nu prime is lower than h nu, all right. The energy of this is lower than the energy of incoming beam, it has to be lower, right. But what it has done is, if secondary X-rays come out of the material, then this leads to a phenomena which is called as X-ray fluorescence. So, this is called as X-ray fluorescence. and this fluorescence is basically they create lot of noise in the system, because you have lot many photons coming out, they go to the detector, they get detected, and as a result they create lot of background in the system. So when this is typically important for so to minimize the absorption of incident beam, you choose an X-ray which has lower absorption in the material. Okay. So for example, in case of copper K alpha edge is 1.54 angstrom, and iron, turns out iron EFEK is nearly lambda FEK is nearly 1.74 angstrom. So which means energy of CuK alpha is higher than energy of FEK, because this lambda is lower, which means when you bombard iron with copper, copper has capacity to excite the K electrons in the iron, K alpha, which means it will create lot of secondary X-rays. So this is secondary X-ray, right? So copper K alpha is not a good X-ray source to be used for iron containing materials, because it gives rise to high X-ray fluorescence, because energy of CuK alpha radiation is higher than K absorption edge of iron. As a result, the X-rays get absorbed in emitting secondary X-rays, and they lead to higher noise in the data, and hence weak signal of the X-ray pattern. So if you want to use, so you have to choose a radiation for iron containing materials whose wavelength is higher than the wavelength of iron. So for these we choose, for example, cobalt K alpha. Cobalt K alpha has a lambda which is 1.789 angstrom. So this lambda is lower than is higher than the lambda of iron, which is FeK alpha, which is, as I said, 1.743 angstrom. So which means the energy of CuK alpha is lower than energy of FeK. So there will be no absorption. Okay. So basically the same concept of the absorption edge. So you can use this knowledge of absorption edge with respect to the incident radiation in different ways. You can choose appropriate filter to filter out K beta, but at the same time you can choose an appropriate radiation which will not lead to background radiation in the form of secondary X-rays out of the incident material, okay, or out of the material which you are using for analysis. So basically these are two uses of knowledge of absorption edge. So for nickel, as I said, we use, for copper CuK alpha we use nickel filters, and there are other materials for which we use different filters. So now let me give you the wavelength of various radiations that we use. For example, the wavelength that we get is about 0.71 angstrom. Cu we have about 1.54 angstrom. Copper, cobalt we have 1.79 angstrom. Iron we have about 1.94 angstrom, and chromium is about 2.29 angstrom. So if you have iron containing material, we typically use cobalt or chromium. We don't use copper. So that is how you choose. So, but what it requires is operator needs to change the source of X-rays. So there is a gun which has a filament is fixed. Oh, so the filament and the target is fixed. Either it's copper target or chromium target or small e target, which means you need to change the gun every time you make this measurement. So, some system, ours I think some systems have both iron and copper and chromium targets, some systems have only copper targets. So, you have to live with that and appropriately. Okay, so this is about the X-rays. Now, let us move on to the diffraction. So, now diffraction, when light encounters any obstacle, well, slit is an obstacle, atoms are obstacles. Now, depending upon whether they have periodicity or not, light will get scattered or diffracted. So, there is a difference between diffraction and scattering. Diffraction leads to effect. So, when you have a periodic, so diffraction, let us say, versus scattering. Diffraction happens in specific directions along which constructive interference takes place, okay, along which constructive interference occurs. Whereas scattering on the other hand is, it is random, it takes place in all the directions, right. So, in what happens here is when the X-rays encounter when a radiation encounters a material which is periodic in nature, and the diffraction leads to, for example, this is constructive interference, certain angle, in this there is no diffraction. So, you will have sort of maxima, minima, maxima, minima, this kind of thing, okay. So, you will have this kind of thing. So, wherever you have peaks, you have constructive interference, wherever you have valleys, you have destructive interference, and this is as a function of spacing or angle, okay. Whereas, in this case, when radiation encounters an object which may be non-periodic, then you have a scattering in all the directions, very weak effect is observed, okay. So, you will have a sort of broad hump kind of thing as a function of spacing or angle. You will not have a particular constructive or destructive interference.
So are they different on the basis of the size of the object?
So, size of the object is going to determine size of the, so whether the diffraction will take place or not, size of the object will determine the wavelength. So, if you choose appropriate wavelength depending upon the size of the slit spacing, then potentially it will diffract. But if slits are randomly placed all over the place, then they do not reinforce, they just cancel it, they interfere in such a manner so that there is no constructive interference.
I want to ask then the size of the object here in case of scattering.
Size of the object means size of the material?
The object,
the atoms.
the atoms. Okay.
I mean, atoms have a spacing, right?
For scattering, we can talk about the atom.
Yeah, every atom. So, if you just have single atom, a single atom will scatter. A single atom will scatter, but the effect will be weaker. But it's only when you have multiple effects. So, if you want to talk about the number of slits that you can have in the system, so you can have one slit, you can have two atoms, you can have multiple number of atoms, and this is basically changing the number of slits. When you change the number of slits in a or you change the number of atoms in a material, then the diffraction effects become stronger. So, this will give you one broad peak, this will give you a sharp peak, this will give you even more sharp peak. So, the sharpness of X-ray diffraction pattern, there is a whole analysis on the intensity as a function of a number of slits. So, as the number of slits increase, the X-ray envelope, the envelope of reinforced beams become sharper as a function of number of slits. So, when the number of slits go up, it becomes very sharp. So, size of the atom does not matter, size of the atom does not matter, the size of the atom is same as nearly same as that the wavelength of diffraction. But so that is what you see. So if you have a nanomaterial and if you have a normal material, a nanomaterial gives you a diffraction pattern which has a broad peak, but if you look at the normal material, it gives you a sharp peak. So this is what is the difference. So this is basically number of slits. Number of slits are increasing. As the number of slits increase with the same spacing, the peaks get sharper, and there is a whole physics behind this. So basically, it says that your X-ray envelope gets more and more sharper as your number of slits increase. I unfortunately cannot go into details of that, but there is a whole analysis behind that. So basically, when you have a scattering, you have beams going in all over the directions. This is scattering, and if you have crystal which is diffracting, so let us say this is the aperiodic crystal, or just a scattering over a particle, and when you have, so you have specific directions along which, so this is constructively interfered beams. So only at these positions you will have diffraction which is occurring. Okay. Constructive destructive interference, I am sure you know from basic physics, so let us not get into that. So the diffraction, there is a whole lot of physics of diffraction as far as crystals are concerned. One can talk about diffraction from crystals in a using a reciprocal lattice model. So where you need to talk about the reciprocal lattice vectors, because lambda is just a scalar property, okay, but diffraction phenomena itself is a directional phenomena. So if you want, so it is appropriate to represent the X-rays in the form of vectors, and that is where we use a quantity which is called as wave vector. Wave vector is reciprocal of wavelength. But if you want to use the wave vector, then even for the lattice you cannot use the normal lattice vector, you have to use the reciprocal lattice vectors, and that is where one deals with Laue equations and evolved sphere. We will not get into details. One neat way of evaluating X-ray diffraction through crystals is via Bragg's law, which puts it very simply, using without the use of vectors as such. So let us now look at what is Bragg's law. So we will perhaps take this up in the next class because we have the time running out. So we will start with the Bragg's law in the next class, and then we will look at the diffraction intricacies through the crystals. Okay.